we had exactly this kind of thing with tiles, and we were doing a situation where all the letters were different. So the thing that makes pepper more difficult than what we did last class is that there is a bunch of repeated letters. So P is repeated 3 times, there's 3 P's in pepper, and E is repeated 2 times. Nevertheless, you can still do the problem. You just have to take what we did last class and add on to it. So one way to do it, let's bring over the blackboard. One way to sort of do it, and switch to the right kind of thing. Okay, so last time we were doing these combinations and permutations. So there's a few different ways you could do pepper. I'll give you some options and you pick your favorite. So option 1, which is this is the narrow tree way. Narrow tree. In order for you to get pepper exactly right, you sort of have to, as you pull the tiles out of the bag one by one, they have to be exactly in pepper. So you have to get the first tile right, or else you are wrong. So right, wrong. What is the chance the first tile is right? Think about that. Then what is the chance the second tile is right? Think about that. And the thing is, because there are repeated letters, the probabilities are different than what they were before. So So this is idea number 1. I guess I already called it option 1. Let's stick with option 1. And so that kind of goes along with the very, very first thing we did way over here for the narrow tree. For right and wrong, last class it was a quarter, a third, a half, and 1. And so that was very easy. With pepper, it's a little more complicated, but you can still get the probability that way, and you'll get something else on the top. Option 2 is use groupings. And groupings was this idea we did before, which is when you want to do ace, king, queen, right? You group together the situations where they are the same cards but in a different order. And we saw that one unordered way was the same as many ordered ways, and we know how to count those. Those were like things like 3 times 2 times 1 in each group. And so in pepper, you can imagine all the tiles are labeled. Imagine the tiles are labeled. So pepper really is P1, E2, P3, P4, E5, R6. So if the tiles are numbered 1 to 6, it's just that tiles 1, 3, and 4 say P, and so on. Then how many ways can you shuffle these around so it still says pepper? Well, let's do another one. For example, P3, E2, P1, P4, E5, R6. This is, I've swapped. You see I've swapped these 2 P's, but it still says pepper. So in other words, if you think of the tiles as ordered, they have to be in order, and the order matters, then there are 6 factorial ways, 6 factorial ordered ways. And pepper is a sort of, it's not fully unordered, but the order amongst the P's, for example, doesn't matter. So you can swap the P's around, and it looks exactly the same as pepper. And the question is, how many ways can you swap the P's? How many ways can the P's be shuffled? And that is the kind of thing we answered last time. And that'll tell you how big this group is. I will say, in addition to the P's, there's something else you have to watch out for. What else do you have to watch out for, other than shuffling the P's around? Yeah. The E's. Yeah, very good. Same question with the E's. How many ways can the E's be shuffled? Okay, and if you can answer both of these questions, how many ways can the P's be shuffled and how many ways can the E's be shuffled, then you can figure out how many different ways in total you can shuffle around all the letters all together to get pepper. And this is the kind of thing we did last time. So this pepper problem really is like, take what we did before and build up a little bit to do that. Okay, that's my hint. Now I'm going to let you guys try it and see how it goes. Any questions or comments before I set people loose? All right, let's see if you're able to do it with those hints and picking which way you want to do it. I'll open this up. Let's give you 2 minutes and give it a try. Okay, and maybe I will try to leave the board up. Okay, it looks like some people are still answering. I'm going to bump this up to 30 seconds, but then we're really going to take it up. All right, let's see how everyone did. Pepper, how many ways? Okay, so one way, this is what we did last time. If all the letters in pepper were unique, if it was a word like list, like we did last class, then there would only be one way. But because of the repeated letters, it's going to be more than one. How much more will it be? Some people said 3, 6, 9, 10, 12, very popular. What else do we got? 60, also very popular. Maybe you, if you wrote this, maybe you calculated the whole probability and didn't see the divided by 6 factorial on the bottom there. And some people said does not exist. Very good. The right answer is 12. So 65% of people got it right. Why is it 12? That's because of counting the P's and the E's. So how many ways can the P's be shuffled? There are 3 P's, and you can shuffle the 3 P's around in any order. That is 3 factorial ways, also known as 3 times 2 times 1. Right? There's that. Which letter is going to go first? There are 3 choices. It could be the 1, the 3, or the 4. And then once you have decided who goes first, there's 2 choices for who goes second. There's 2 tiles left. Choose one of them to go there. And then the last one is forced. So 3 times 2 times 1. When you have these sort of choices, you multiply them. And we saw that from the big tree happening last time. So how many ways can the P's be shuffled? It's 3 factorial, also known as 6. How many ways can the E's be shuffled? So the E's can also either appear in their original order, E2, E5, or they could be swapped, E5, E2. There's 2 ways, but that 2 really is a 2 factorial, 2 times 1, which is 2. And then last but not least, you can combine any shuffling of the P's with any shuffling of the E's to get any, that would be a valid way to make pepper. So therefore, number of ways to make pepper, it's going to be the product, 6 times 2 is 6 times 2 equals 12. So if you think of the tiles as being numbered and coming in where order matters, there's 12 different ordering of these numbered tiles that all spell pepper. And so the answer is 12 over 6 factorial. Therefore, probability says pepper equals 12 over 6 factorial. This is the kind of thing we did last time. The number of order matters ways. And then 12 is the number that are pepper. Okay. So that's a perfectly good valid answer. I think that's the easiest sort of way to think about it. And there are many variations of this. In your homework, you'll have problems that are like this. And this is kind of like a bread and butter topic in probability classes, is these kinds of counting and shuffling and things like that. Any questions or comments about that method of doing it? Let's see also let me quickly draw out the probability tree. The probability tree is going to have the same kind of thing. The probability for that first thing to get the first letter right, it's not 1 out of 6 because there's 3 P's in the bag. So the probability of the first one being right is 3 out of 6, and it's wrong 3 out of 6 times. And then the next letter being right, there's 2 E's in the bag. So this is 3 P's. Then there's 2 E's in the bag. So that's 2 out of 6, and 4 out of 6 to be wrong. And then you can keep going. There's 2 P's left in the bag. So you have a 2. Let me actually color code. Let me try to color code these E's so we see the E's and the P's are different. There's a 2 out of 6 for the next P. Next P. Oh, okay. Let me zoom in a bit. The next P is 2 out of 6 to be right and 4 out of 6 to be wrong. And then we need yet another P, which will only have a 1 out of 6 chance because at this point there's only 1 P left in our bag, the last P. Then there's 1 E, which has a 1 out of 6. And then the last thing is that R, that's going to happen correctly. I keep writing out of 6, but that's not right, is it? Because the number of tiles left in the bag also decreases. So it's not 2 out of 6, it's 2 out of 5. 2 out of 5. Let me fix the denominators that I've written incorrectly. Okay, so this is the problem with these tree things, is they take up a lot of room if you want to really fully write them out. 2 out of 4, 1 out of 3, 1 out of 2, and then the last tile is 1 out of 1. That one, there's only one tile left. But these are the probabilities to be correct. So the total probability of get pepper, is the probability multiplication rule along the top there. It is 3 out of 6. Then it's 2 out of 5 for the E. Then it is 2 out of 4 for the next P, 1 out of 3 for the last P, and 1 out of 2 for the E, and 1 out of 1 for the R, and all of these things get multiplied. And the reason I'm showing you this is because you can see in here, there's the 3 factorial, 3 times 2 times 1, and the 2 factorial, 2 times 1. So it's exactly the same solution as we had before, but in this one we're sort of counting it up first, and in this one we're kind of doing probabilities as we go and combining the probabilities and the counting. But they really are the same solution and the same answer. So these 3 together, that is 3 factorial for P's, and then these 2 together, that is a 2 factorial for E's, and that is another perfectly good way to do it and to see the answer. Okay. Any questions or comments now about either of those methods? Yes. Yeah. I was doing the 6, 5, 4, 3, 2, 1 wrong. Yes. Okay. Very good. Yes. Okay. Let me mention there is one other way that some people like and comes up somewhere. This is option 3. And in option 3, you always think of things as unordered. So you don't do this trick with the P's and the E's and thinking of them as being shuffled around. You always think only in terms of unordered sets. And so you ask the question, how many words can we make? Let's put option 3 down here. Which is, let's ask a question, how many different words, or let's say letter sequences can be made with the letters. And in this one, what I would do is I would say, okay, I got my 3 P's over here, my 3 P tiles, my 2 E tiles, and my R tile, and I'm trying to slot them into 6 slots. So these are the letter slots. Okay, and the first question I could ask is, I got my 3 P's, I'm going to put them somewhere amongst these 6 slots. How many ways can I do that? So where to put the P's? Where to put the P's? And this is something we have already done. So if you try to calculate where could the P's go, sort of from first principles, it will take you a little bit. But if you remember the formula, it is 6, choose 3. There's 6 slots, choose 3 of these slots to put P's in. That's what the choose means. Okay, this is the binomial coefficient. So that's to do the P's. Once the P's are in, we can ask the question, where to put the E's? Where to put E's? And now, after we put the P's in, so 3 of the slots will be taken up by P's, maybe this one, and this one. Where could we put the E's? Well, there's 3 slots left. We got 2 E's, so 3 choose 2. So this is once you get sort of practice with this choose notation, it kind of does what it says on the tin. 3 slots, choose 2 of them to put the E's in, 3 choose 2. And then last but not least, you got to put that R somewhere. There's only 1 slot left and 1 R, so the R is sort of forced. It goes in the last slot. 1 choose 1. Okay, and if you multiply all this out, this will be 6 factorial over 3 factorial, 3 factorial times 3 factorial over 2 factorial, 1 factorial, and times 1. And then there's a bunch of nice cancellations. The 3's cancel, and you end up with 6 factorial over 3 factorial times 2 factorial, also known as 6 factorial divided by 12. That's what we got. So that's the number of different possible words you can make with these letters by choosing where they go sort of in order. And therefore, the probability that you get exactly the word pepper, that you get pepper, well, there's only one word if you think of them as unordered that spells pepper. And how many total possible words are there? There's that many. So it's 1 divided by the number of words number of, let's call them unordered words. So it's 1 divided by this silly number, 6 factorial divided by 12, also known as 12 over 6 factorial, which is what we got with the other two methods. So some people prefer this method, and this kind of thing is sometimes called a multinomial coefficient. So just choosing one, like 1 n choose k is a binomial coefficient. When you multiply them all together like this and get this kind of thing, it's called a multinomial coefficient. We're not going to be big on multinomial coefficients, but if you're into that, you can tell your friends. Multinomial coefficient. So when you multiply them all together like this, you get this kind of number. Okay, that's the same problem done 3 different ways. We've done it to death. Any questions or comments about these methods? Let's do a quick show of hands. Which method is your favorite? Who likes option 1 the best, the narrow tree? Oh yeah, option 1 pretty popular. Who likes option 2 the best, shuffling stuff around? And who likes option 3 the best? Okay, option 3, the least popular, the most exotic of the options. Okay, I think that is all we have to say about permutations and combinations and mixing stuff up for now. There's gonna be lots of homework due on Friday, and there'll be midterm problems about this as well. This is sort of like a staple topic in probability. Any last second questions or comments? All right, I'm gonna turn it over to Professor Humphrey, who I think is gonna tell you more hard stuff about EARNs. Is that right?
Well, I'm not saying it's hard stuff, but more stuff. Yes, I won't say it's hard stuff.
Do you want the HDMI? I think your microphone might be on the ground.
Oh, that makes a lot of difference. I'm stepping on my microphone. These clips are useless, but nonetheless, we'll try to get it to go. Okay, let's go to HDMI. Okay, so I left these one day questions to try on your own. And I don't know whether people tried them on their own. A bunch of them are pretty easy. I won't go through for taking them up. But, and the width replacement case is pretty easy in lots of ways because we end up with independence. And this question here, what is the probability the second ball drawn was red? If we don't know the color of the first ball, was taken up in class previously as well, where we found that the probability that the second ball is red, if we don't actually know the color of the first ball drawn, even when we sample without replacement, was equivalent to just sampling the first ball. Same probability there. And we kind of put that together. Now, this question here, if it is known that at least one ball drawn is red, what is the probability that both balls drawn are red is a little more complicated. And we can attack that multiple ways, and I want to make sure that everybody is on top of that particular question. And we're going to work that one out right at the moment. And okay, so again, our events, let's see, what color of pen would we like to use? Well, maybe black. Let's just see if that's a good black. Okay, so our events. And R2 is second ball drawn. And more compact notation. I'm just going to mention the notation a little bit here because we need to always be able to expand our notation. More compact. and in this case, I equals 1 and 2. So the idea of this, yes, it's easy to just put an R1 and R2 in this case, but if we wanted to draw a whole bunch of balls, it would be nice to have something that doesn't require that I'd say, here's R1, R2, or here's R3, etc. We've just got a more compact notation. So let's go back to what that question was. If it is known that at least one ball drawn is red, what is the probability that both balls drawn are red? So this is what we've got to be able to do is translate this to a probability statement. And what we know, so hey, just what happened there? What happened there?
Do you want the dock hammer, or do you want the...
Well, I want that, and I want
you want
the question on the other side. That's what I want.
All right,
Okay, question on the other side. Work with this for the moment. And so we're going to find probability. I want to write this out again, that at least one ball just like a probability, I'm rewriting it is. It is known. So I'm going to rewrite it. What is the probability that, that both balls drawn are red? Given at least one ball drawn is red. So that is worded differently than the way it is worded on the slide there, but it's exactly the same question. Okay, so what do we know? Both R1 and R2 occur sorry. No, that's not what we know. No, we don't know that. That's R1 union R2. And so what we want to know is the probability of R1 intersect R2 given R1 union R2. That's looking nice. You agree that's looking nice? Okay, looks messy. Looks messy. Okay, so let's kind of think about this in terms of our probability tree. We'll also take a look at it as a Venn diagram. We can do that as well. So going back to our probability tree. And we are sampling without replacement. And okay, we went through, we got R1, we got R1 complement, and this was 3 out of 5, 2 out of 5. And then we went to our second pole, and we had R2, and this was 2 out of 4, and that was the probability of R2 given R1. When we labeled this was just the probability of R1, and we did this. And I'm kind of just doing this very thoroughly just so that we're all comfortable with how the pieces are going to get pulled together. And that was R2 complement, or you could call it the probability of a white if you wish. And we did this one. And so this is R2. This is going to be the probability of R1 complement. And this was R2 and R2. What was the probability of getting a red on the second, given I got a white on the first? It was 3 out of 4. 3 out of 4. So that was the probability of R2 given R1 complement. And then the probability of getting a white on the second, which is didn't get a red on the second, given I didn't get a red on the first. In other words, I got 2 whites in a row. That was 1 out of 4. And that was the probability of R2 complement given R1 complement. We got all that kind of did. And then we went through, we multiplied out the intersections. And I won't go through the all the notation, but we kind of just went along and got the various intersections. And we came out with, well, if we want to just put them in here, R1 intersect R2 was 3/5 times 2/4. We ended up with 6 out of 20. And so on, we could go down and get all of the various intersections. Uh, 6 out of 20. Probability of R1 complement intersect R2 was also 6 out of 20. And the probability of R1 complement intersect R2 complement was 1 out of 20. And of course, those all add up to 1. A good check, just a check. Now,
Do they add up to 1? What's that?
So just a second. What have I done? 6 because that should be 2 out of 20. Yes, that's 2 out of 20. Yes, glad you checked that. 6, 6, 6, 18 plus 2, 20. 20 out of 20. You could move them to tenths if you wish. Okay, well, why not? We'll go to tenths. No need for extra messy fractions. Okay, so we could attack the question like this. We're going to do this. I'm also going to do a Venn diagram of this one, though. Let's do a Venn diagram, just showing that we can translate the probability tree to a Venn diagram. And draw our sample space. There's R1, not necessarily to scale here. R1 had a probability of 3/5. And then there was R2. And it kind of went like this, more or less. The point is there is an intersection there. And that intersection, R1 intersect R2, this was 3/10. Okay, so there's R1 intersect R2. And let's see what else we've got. We've got R1 intersect R2 complement. Okay, so we got a red on the first, but we didn't get a red on the second. And 3/5 is 6 out of 10, 6 out of 10. So this area here is 3 out of 10, or we could have got it by direct multiplication. And this one here, R2, well, I haven't said what R2 is yet. Let's leave that one for the moment. Well, what did we get? We got the area where R1 occurred and R2 did, or R1 didn't occur and R2 did occur. We worked that out to be 3 out of 10. And, so that is R1 complement intersect R2. But what we see is that, in fact, the probability of R2 is just the sum of those two intersections there. And that's 6 out of 20. So that turned out to be, 6 out of 10. That also turned out to be 3 out of 5. Okay, so R1 and R2 were the same. The unconditional probabilities were the same. And are they independent? No. We were sampling without replacement. If they were independent, this intersection would be 3/5 times 3/5, which would be 9 out of 25. But it isn't 9 out of 25. It's 3 out of 10. That's a different number. And this area out here was the probability of R1 complement intersect R2 complement, and that was 1 out of 10. Okay, so everything that we've mapped onto this Venn diagram here is the same as what we worked on the probability tree here. Okay, so now let's go back to our original question. So find the probability of R1 intersect R2 given R1 union R2. So let's just kind of go through this statement to make sure that this is in fact what we want. We are given that at least one of the balls is red, okay? And that is the union of R1 or R2, okay? Here at least one of the balls is red. Here's at least one of the balls is red. In fact, both of them are red. And here's where at least one of the balls is red. The second is red, but the first is not. This doesn't get included because both of them are white. Okay, well, my goodness. Okay, what do I do with such a messy thing? Well, let's start off by taking the intersection. Remember that the intersection is an event. Remember that the union is an event. And so I'm just going to recall that the probability of A given B is equal to the probability of A intersect B over the probability of B. Basic definition of a conditional probability here. And so what am I going to do with that? Well, I'm going to say, well, that's the, I'm going to take that intersection. I'm going to take R1 intersect R2, and I'm going to intersect it with R1 union R2. And then that's going to be divided by the probability of R1 union R2. Holy crap, what a mess. How's anybody supposed to solve a problem this difficult? It's by just like thinking it through and saying to yourself, where is R1 intersect R2 intersected with R1 union R2? Well, one of the tricks is that the intersection is always included in the union, okay? So the intersection has to be a subset of the union. And so that allows us to simplify this and say this is simply the probability of R1 intersect R2 over the probability of R1 union R2. Ooh. So we simplify because R1 intersect R2 is a subset of R1 union R2. And so when I take a union of a subset with the bigger event, the intersection just falls down to the subset. Okay, so we've got that, and now we're saying, okay, this is kind of straightforward. So if we were to do this, we'd say, okay, probability of R1 intersect R2 is 3 out of 10, and the probability of R1 union R2, a couple ways to go about it. We could just say, it's 3/10 plus 3/10 plus 3/10, 9/10, or we could say the union is everything except this intersection outside the circles, which is 1/10. So it's going to be 3/10 over 9/10 is going to be 1/3. Okay? So one approach, we're going to just go back to the Venn diagram in a second here. Any questions about what I did there? And really the key thing is to note that idea that the intersection of the intersection with the union was simply the intersection. Everybody good on that one? Yeah. It depends on whether it's a multiple choice question of which you have to figure out whether it's A, B, C, D, or E, and so you don't have to show anything, or whether it's a written question where we ask you for a solution, right? And so you kind of got to get the technique of just showing enough work, like the right amount of work that we know where you're thinking, how you're thinking, and that's really, I think the key thing is there is a skill of getting a solution down to the minimal number of steps that show that you know what you're doing versus and not leaving sort of black boxes. Yes. Okay. So I can show you that. We can draw another picture here. So draw another picture here. Just going to do the R1 and the R2. And first of all, I'm just going to shade in the union. Okay. Well, first of all, where was the union? How do I get the union of R1 and R2? I'd say, okay, here's where R1 occurs, and here's where R2 occurs. And any place that has any kind of shading is the union. But cross-hatching is the union. So when you say the intersection of the intersection with the union, you're saying, I need a spot
Wait,
where
what-
both the intersection
Can
occurs.
I have a really embarrassing thing to admit. What does cross-hatching mean?
What does cross-hatching mean?
Is that when it
It
goes
is
both
like
ways?
the lines go this away
Uh-huh.
and this away.
Oh, okay. So then did you mean to write the cross-hatching as the intersection?
Sorry. Yes, I did.
Okay. I thought you're
Yeah.
I
No.
thought I had misunderstood
Yeah.
what cross-hatching
Any
means.
shading is a, yeah, no, that was a brain fart. Yeah, thank you for sorting out my brain fart there. Thank you. That is the intersection. So that is the intersection. And so, again, when we say, okay, where does both the union and the intersection occur? Well, the union occurs anywhere with shading, but the intersection only occurs where we've got the cross-hatching, and so that simply is the part with cross-hatching. Does that make sense? Okay, so that's kind of a cool thing. Okay, so let's go back now to the Venn diagram, and notice this little trick here. That with the probability tree, if I am given at least one is red, where does at least one is red occur? Well, it occurred, actually, let's use this one because this is a red pen. At least one is red occurred here, and here, and here. Didn't occur here. Okay, didn't occur there. And then I say, where was the situation where both of them were red? Well, the situation where both of them were red was only here. Now, I'm not trying to cross that out, but I'm just going to make that kind of like highlight the red. I should have like
that's called cross-hatching.
That's called cross-hatching. It's kind of nice cross-hatching, isn't it? Not too bad. Anyhow, this was the only place where both of them occurred, and so it can't be here. The union was the 9 out of 10, but of that, 3 out of 10 is where both occurred, so we take 3 out of 10 divided by 9 out of 10, and we are left with
Gary, I figured out one advantage of the doc cam over the digital.
What's that?
Which is when someone gives you a conditional probability problem, you can take the probability tree, and they said this one didn't happen, so you can cut that right out of your probability tree, and then you're left with just those 3, and you want the probability of that one out of the whole thing, right?
Okay. So
It's dramatic.
it is dramatic.
Wait, hold on. Let me do it with the Venn diagram. Now I'm excited. So we got the Venn diagram, and we're cutting away everything not in the union. Oh, this is exciting. I hope you weren't saving these, Gary, because now they've been ruined.
They were going to go in my
your personal collection.
papers of things to say for all time in my life.
Look, somebody comes along and says tricky information like you are given that the union occurred. Well, when you're given the union occurred, you take everything not in the union and you throw that right out. And you're left with these. That adds up to 9 out of 10. So the whole thing is going to be out of 9 out of 10.
So you got to rescale.
Was the answer something out of 9 out of 10? It was. I think it was 3 out of 10 out of 9. Maybe I threw that out way too soon.
Okay, so I left out the with replacement case, which was so easy for the first couple problems that you may say it's going to be like super easy in the with replacement case because if R1 and R2 are independent, will R1 intersect R2 be independent of R1 union R2? That is an assumption which students often make. The answer is, well, check it. Okay, I will ask you to check this. Is R1 intersect R2 independent of R1 union R2 in the with replacement case? And that is what we will leave for today.
Okay, make sure you do your homework. See everyone on Monday.